Hi everyone. So today I'm going to talk about an enumeration problem for a certain class of DFAs, that is Deterministic Finite Automata. So this is joint work with Wenjie, Fang and Wallner. Okay, so a DFA for a binary language, AB, binary alphabet, AB, is just a graph in which each vertex, node, or state has two outgoing edges, one labeled A and one labeled B. We also have an initial state Q0 and an explicit set of final states which are drawn in green. So the point is that any such DFA defines a language, and in fact it's known or defined that the languages that are recognized by DFAs are exactly the regular languages. Anyway, so in this case, this is the recognized language. So the reason, for example, why AAB is in the language is that if we could start at the initial state and go AAB, then we enter a final state. And that's the same for all 5 of these words, and these are the only 5 words for which that is the case. For example, AAAB isn't in the set because if we went AAAB, we wouldn't be in a final state. Okay, so the DFAs that we're actually counting here are those that are minimal and acyclic. So minimal means that no DFA with fewer states recognizes the exact same language, and acyclic means that there are no cycles except that there have to be cycles at the sync. That is the sync being a non-accepting state, which which you can't leave. So there have to be some cycles, so we call it acyclic if the only cycles are at a unique sync. Okay, and so the connection with finite languages is that a minimal DFA is acyclic if and only if it recognizes a finite language. Okay, so in this work, we're counting the number of minimal acyclic DFAs on a binary alphabet. So we denote these numbers by mn, or n plus 1 nodes. That means there are n nodes other than the sync. So this problem was studied a bit in computer science literature between 2002 and 2006. But the best bounds were out by at least an exponential factor, and I think the upper bound didn't even have the factorial bit right. So in this work, in previous work, we gave upper and lower bounds which differ just by an n to the 1 on 4 factor by a relationship with another problem that we worked on, that is that of counting compacted trees. So in this work, we've done even better. So in particular, in this work, we've deduced this asymptotic form for the numbers mn. So the factorial, exponential, and polynomial bits are very standard things that you'll see in asymptotic expansions. So the really interesting part of this expansion is the stretched exponential here. So this A1 is this number, which is defined as being the largest root of the area function, which is this mysterious function that I'll talk a bit more about on the next slide. So theta means that we don't know this up to a constant term, or even so we have upper and lower bounds which differ just by a constant term, but we don't even know that a constant term exists. So naturally we conjecture that that this is the asymptotic form, where we have this approximation of gamma, which we expect to be correct to the digits quoted. Okay, so what was the area function? So the area function, as I said, is defined by this integral. The largest root is this blue point, as you can see. It can also be defined as being a solution to this differential equation, which goes to 0 as x goes to infinity. So the array function has appeared a few times in enumerative combinatorics before, although not quite as directly as it will appear for us here. Okay, so the first step in our proof is a bijection to decorated paths. So we have a bijection from DFAs to something that's easier to count. Okay, so first of all, we do a depth first search of the DFA, where we prioritize A edges over B edges. And so what that means is that for each vertex in the DFA, if we draw the black path from Q0 to that vertex, it will be the first path from Q0 to that vertex or state. It will be the first one in lexicographic order. So, for example, going here, we have AA, which is clearly the first in lexicographic order, which ends at this vertex. Like another path there would be B, 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 which is later in lexicographic order. Okay, so we'll color the other edges red. And since we have this tree structure, we can draw it really as a binary tree. Okay, so now we're drawing this in a way such that the left edge is always an A edge, and the right edge for each vertex is labeled B. But we can even forget about the labels. Okay, we also number the vertices in post order, and so what that means is the vertices on the left will always have lower labels than those on the right, which have lower labels than the vertex, the root vertex itself. And so the point is that then by construction of the tree, the red edges always point from a larger labeled state to a lower labeled state. Okay, so we want to get rid of these red edges, so we're just going to label we're just going to turn them into pointers, each labeled by the number that they point to. So this is a 3 because it points to a 3. Here we have something pointing to a 5, which becomes a 5. All right. So now we have a tree, and so there are plenty of ways to biject a tree into a dig path, which is what we do here. So we draw a traversal in blue outside of the tree, around the outside of the tree. And so this is going to, okay, and so whenever this passes a red pointer, we add a horizontal step, and so on. And so in each case, we put a cross below the horizontal step based on the label of the pointer. So these were all just 1s, so we have crosses at height 1. Now whenever we go up, we do an up step, and we color the up step with the color of the corresponding state. So we go up again, and get a white up step. Now we pass a couple more pointers, so in this case we get a cross in row 3 and then a cross in row 1 because of these numbers, and so on. And so you can see that the up steps actually go in the order, like in each case the state corresponding to the up step, or in this example, is the same as the number of the row of the up step. Okay, so we now have this path which starts at -1, 0 and ends at nn. So the path, the only properties of the path are that it stays below the diagonal. One box is marked below each horizontal step, and each vertical step is colored green or white. So then by the bijection, the number of these paths is the same as the number of acyclic DFAs in a binary language with n+1 nodes. Okay, and so then we can get a recurrence for these paths. And it's just for each horizontal step, there's just m choices, where m is the number of boxes below. There are 2 choices for each up step, so we get a simple recurrence for these numbers, where a and m is the number of these paths ending at the point nm. Okay, so by the bijection, a and n is the number of acyclic DFAs. Okay, but hang on, we wanted to count minimal acyclic DFAs. Fortunately, minimality turns up quite nicely here. So for a DFA to be minimal, we just have to make sure that whenever we get to a new state, it can't be an exact copy of an old state. So this is really only possible when we pass a leaf. For example, here, we could, if we make these 2 pointers 1s, then this would be an exact copy of this state. If we do it like this, we'd be exactly copying this state. And if we do it like this, with a 1 and a 2, then we'd be exactly copying this state. So that would mean that the DFA wasn't minimal, because we would be able to, in the DFA, merge the 4 and 3 and create a DFA with the same, which accepted the same language. Okay, so all that means is that when we create a new leaf, which is numbered m, which is labeled m plus 1, there are m choices for the leaf which we have to avoid. Now in the path, a leaf corresponds to a right step, then a right step, then an up step. And so it just means we need to avoid m things whenever we have a right, up. Okay, so we can write this directly into the recurrence. So the n minus 2, n minus 1 coming from the fact that we go right, up. And then by the bijection, mn is now just bnn, number of paths ending at nn. So that is, bnn is the number of minimal acyclic DFAs with n plus 1 modes. Okay, so we have this bijection. We have this recurrence, which determines mn. And so now we can forget about the problem with the combinatorics of the problem we were working on and just analyze the recurrence. Okay, so the first thing we do is we just transform numbers b, n, m using this equation into these ENMs. And then the new recurrence is this. And mn is related to e2 and 0. So this is just convenient because we cancel out like some of the factorial factors from the Bn and from the asymptotics. Okay, and so before the steps we had were right and up, whereas now we have well, up and down steps, which always go to the right. Okay, so the first step in analyzing the recurrence is to do some heuristics. So recall we have this recurrence for A and M, and all we need to do now is to understand how E and M behaves for large n. So this is a plot of the values for E and M for a fixed value of n equals 100. This is a plot for n equals 1000. And so you can see that all the interesting stuff is happening on the left. So let's zoom into the left. Okay, so now that we've zoomed in, you can see the x-axis only goes up to 18 here, I guess. Now that we've zoomed in, these look like they might be converging to something. In fact, if we draw so this is now for n equals 2000, you can see that it really does look like it's converging to some sort of curve like this. Okay, so let's guess that it really is converging to this curve. Of course, the convergence requires that we rescale the x-axis and y-axis by some functions gn and hn. And so if this convergence is really happening, it means that E and M is approximately hn times f of m plus 1 over gn. You can see that m plus 1 over gn is kind of the relevant point on this axis, and yeah, we get the Hn because of this factor. Moreover, we can guess from the heuristics, or just by trying this for a few values, that Gn, the correct choice for Gn is cube root of n. So we have this guess now for E of n. Okay, so we've got this recurrence, which we want to solve, at least asymptotically, and we have this guess. But we still want to figure out what h of n and f of x are. So what we do is, we just, as you would expect, substitute this guess into the recurrence. Now we'll get a h of n on the left and a h of n minus 1 on the right. So taking the ratio of those and then expanding the rest of the stuff as a series in n. Sorry, so we substitute n equals this first, so that the stuff inside the f becomes just kappa. So then expanding this ratio as a series in around n equals infinity, we get this series. Okay, and then since this is just a ratio of n's, this ratio can't depend on kappa, so this has to be a constant. Okay, so assuming that this is actually equal, or sort of sufficiently equal up to 1 on n, we must have these two equalities. So where c is the value of this constant. Okay, and so each of these, so the first of these gives us directly the asymptotic form of Hn by this definition of Sn, and this is exactly the differential equation for the area function, shifted to some extent. But okay, so we can already see this stretched exponential appearing. Yeah, so we haven't, so now we still need to determine this constant c, which we can do just from the fact that f of 0 equals 0. So the reason for that is that we know that if when m equals minus 1, well, the E of nm's are only defined for m positive, so for m equals minus 1 we get 0. So hence f of 0 equals 0. So from f of 0 equals 0, plugging that in here, we get that c equals, yeah, that c must be something like this, where a1 is a root of the area function. And in fact, a1 is going to have to be the largest root of the area function for f of kappa to be positive, or positive kappa. Okay, so we get, so to summarize, when we make this guess, we get these estimates for h of n and f of kappa. In fact, we can refine this a bit by guessing the next order term, and that yields a more precise estimate for h, which in fact even involves the polynomial term. And so this way we conjecture this exact asymptotic form for Mn, because, yeah, coming from this guess for En, and the guess values of h and f. Okay, so I'm just going to quickly say a couple of things about the inductive proof. So the idea is that we want to prove some bounds on E and K using some A and B for all sufficiently large n. Yeah, for all K and all sufficiently large n. So the way we find this A and B is we use the heuristics to decide on forms for them. Then we fiddle with the form of A and B until they satisfy the recurrence with the equality replaced by inequalities. And finally, we can prove the inequalities by induction. Okay, there are quite a few technicalities that I'm skipping over here. I guess you can pause the video if you want to, read this slide properly. But anyway, in summary, these were the main steps in proving the lower bound and similarly the upper bound. So we have a lower and upper asymptotic bound for the numbers Mn of minimal acyclic automata, DFAs recognizing a binary language. And yeah, so this is the final theorem, and here are some further problems. So, any questions?